In this video, I want to take a look at what happens when you're solving an Euler equation and your quadratic equation has only one solution. So here we go. I should point out, and I should have pointed this out in the last video as well, that I'm currently working only with positive values of x, because what does it mean to say y equals x to the r if x is a negative number, right? If r is an integer, that's fine. But when r is not an integer, like say a half, what does it mean to have minus 1 to the half power? Well, you get complex numbers really quickly. And so for the moment, I'm only dealing with positive x values. We will deal with the negatives in next video or the one after that. Anyway, so here's what I'm looking at. I'm looking at a Euler equation, and that has a corresponding quadratic equation that you're solving when you're trying to find solutions of the form y equals x to the r. The question is, what happens when this has only a single solution? Well, this is only a single solution. It means it factors into x minus that solution, sorry, r minus that solution times r minus that solution again. So multiply this out, it looks like this. So we're saying that this equation is supposed to look like that one. So the negative 2a is the alpha minus 1, which means alpha is 1 minus 2a. And the beta here is that a squared. So when the Euler equation looks like this, it's only giving us one equation and one solution, that is y equals x to the a. The question is, what's the other solution? Okay. Well, we have a way of finding other solutions. In fact, earlier this quarter, when we learned about both Abel's theorem and reduction of order, there were several homework problems that actually were, you go back and look at them, when they gave you one solution to an equation and asked for other, quite often that the equation was an Euler equation. So anyway, to find the other, I am going to use Abel's theorem. Okay. So first thing I need to do is I need to divide by that x squared to get a 1 in front of the y double prime. So the x cancels out, one of the x's cancels out there, and you got an a squared over x squared here. So Abel's theorem says that the Wronskian of two solutions is going to be equal to some constant times the integral, e to the integral of minus p of t dt, or in this case p of x dx. Rp is 1 minus 2a over x. So I integrate that, I get e to the 2a minus 1. The minus I got distributed in there, right? And the integral of 1 over x is the natural log of x. Again, don't worry about the absolute value sign because x, I'm assuming, is positive right now. This simplifies to x to the 2a minus 1. I should also point out that Abel's theorem says that there's a constant out in front here, and I'm just choosing the constant to be 1. So I am looking for a solution here. I'm looking for y2, knowing that y1 equals x to the a. So I'm plugging that in here, calculating the Wronskian of x to the a and y2. The derivative, of course, would be ax to the a minus 1. What the heck is this a doing here? Now it's gone. So I need this Wronskian equal to that calculated value there. Taking the determinant, I've got this. So x to the a times y2 prime minus y2 times ax to the a minus 1. This is a first order linear differential equation. So I'm going to solve it by the methods from, heck, day 2 of this quarter, right? Divide both sides by x to the a to get the y2 prime with a 1 in front of it. The x to the a minus 1 divided by x to the a is just x to the minus 1. And this one here, x to the 2a minus 1 divided by that x to the a is just x to the a minus 1. So the integrating factor for this equation is e to the integral of this minus a x to the minus 1, which is x to the minus a. So if I multiply both sides by x to the minus a and integrate, then this side is just y2 times x to the minus a, and this is the integral of x to the minus 1 dx, which is the natural log. And then you multiply both sides by x to the a, and you get x to the a natural log x. So the other solution is just the solution you already had times the natural log of x. So the general solution looks like c1 x to the a plus c2 x to the a log x. Let's do one example. I've got this equation right here. Assuming that the solution is going to look like y equals x to the r, I can plug it in and I end up with this quadratic equation, which is this right here, r squared minus 6r plus 5, no, plus 9 equals 0. This factors into an r minus 3 and an r minus 3, so r equals 3 is the only solution, which would give me x to the 3 as my, sorry, r equals 3 is the only solution to that quadratic equation, so x to the 3 is the solution to the differential equation. And what we just did up above is to say that the other solution is x cubed times log x. So there's the general solution to this equation. c1 x cubed plus c2 x cubed log x. That would be natural log of x, of course. So there's one more thing we need to do in regards to these Euler equations, and that is what happens when the solutions to your quadratic equation are actually imaginary or complex numbers. Okay, we will do that in the next video.